Consider that we take our system, and here just simplified for visualization purposes, it's the 2D system, and we translate it. We move the whole thing over by an infinitesimal amount in the x direction. Didn't change anything in the relative positions or anything, but just moved the whole thing over. And say that suppose our system was completely unchanged by that. By another theorem, then in the x direction is, say we translate it in the x direction by an amount epsilon. Then our position vector will translate to x plus epsilon y z, which is just x y z plus epsilon 1 0 0, which is just the x basis vector. Alright. That means that this will be our q sub I, our q vector of E. When you take E goes to 0, that's just a 1, so the limit doesn't really do anything. And it's just going to be our position basis vector. Now we can always write I should have mentioned this first, is just the dot product of the Lagrangian divided by each, or the derivative of the Lagrangian partial derivative with respect to each x dot. So with x dot, y dot, z dot are the components of that. Dot producted with, I don't need the e, or the I, as a vector. And in our case, this vector is represented by that, and we can write it in terms of the basis vectors. So you're going to dot this whole thing with this vector, which is just EX. Well, these are orthogonal, so these are going to go to 0. And these are orthonormal, so they'll go to 1. And we learned that if our system is unchanged by x translating over to x plus epsilon, that this quantity here is conserved. And when you want to generalize that to any y over y plus epsilon z full translational symmetry, then you'll get a whole vector where the ith component is of this form, and we call this conserved quantity in this situation momentum. And this definition, this redefinition, is part of the inspiration behind the Hamiltonian formulation. Hamiltonian just turns out to be energy, but yeah, there we go.